Good evening, everyone, and welcome to the first interactive session for Soil Mechanics 1 course. I hope everybody is doing well. My name is Saida Said, and I am one of the TAs for this course. I am a research scholar at IIT Roorkee, and I'm a part of the PMRF program. This is my collaboration with NPTEL. I'll be taking weekly interactive sessions for this course in which we will do some questions based on whatever you have studied in the previous class, previous week. So, as per my knowledge right now, you have completed 1 week of this course, and in this 1 week, as far as I could see, you have studied classification or types of soils, and you have studied the rock cycle and formation of soils. So these are all theoretical concepts. Because we will be doing numerical questions here, I'll be focusing more on the numerical part. Uh, Also, I could see you have done the classification of soils, in which you have done the sieve analysis. You have done the hydrometric analysis. You have studied the consistency limits. So this is what our first interactive session will be focusing on, some questions based on these topics. Okay, so let's dive in. Okay, so this is the first question. Following are the results of a sieve analysis. You have been given sieve size in mm, and you have to perform the necessary calculations and plot a grain size distribution curve. You have to determine the D10, D30, and D60 from this curve. Calculate the uniformity coefficient and the coefficient of gradation, that is Cu and Cc. So these type of questions in which we have to plot a graph and make these tabular calculations, we will be performing in an Excel sheet. So let me open an Excel sheet for this. This is the interactive session 1, Excel sheet for interactive session 1. Okay. So first let's start with filling in these details. This is our sleeve size in mm. Then we have our mass retained in gram. I can copy this directly. Okay, so let's move forward with this question. Give me a moment. Okay, so this is the mass retained on each sieve, and as you might have studied, what we need is the percentage finer. So what we will do is first we will calculate the cumulative mass retained above each sieve. Okay, so in the first on the first sieve, since the mass retained is 0, so we'll have a 0 here. On the second sieve, we have 21.6 grams, so this is what we will have here. On the third sieve, we will have a sum of all these, so it will be 49.5 plus 21.6. Okay, and on this it will be a sum of this. So we can either write because this is not a worksheet for Excel tutorial. Let me just write the formula, and then we can drag this, and this is what we will have. So this will be our cumulative mass above each C, and this is basically our total mass that we have used for this analysis. Let me give this another color. Okay, so now we let's calculate the percentage retained. Percentage retained is basically percentage with respect to the total mass, which is 450. So let's calculate. It will be 0 over 450 into 100. So this will be our percentage retained, and now we want to calculate the percentage finer than, which is basically percentage passing, which is basically 100 minus our percentage retained. So let's do that. Column B, and this is what we get. Let me write this with fewer decimal points. That's better. Okay, so this is our main column that we want to calculate for our question, in fact, for our classification. And now let us plot a particle size distribution curve. Let me insert a plot. Particle size distribution curve. X value is the diameter in mm, Remember, this has to be a log scale. I will change it in a moment. And the y value is the percentage finer. Okay. Okay. And we will change this to a log scale. Let me reverse the values. Okay. And okay. Should go to 10. Once again. It has to go to only 100. Let the major be 20, minor be 10, and the horizontal axis crosses at 0. Okay. So let's write the label. Okay. Here, vertical axis crosses at 10. Okay. So this is our particle size distribution. Okay. So basically this is our particle size distribution curve for our given soil. So let's go back to the question and see what it is asking us. Perform the necessary calculations that we have done. Plot the grain size distribution curve that also we have done. Determine the D10, D30 and D60. Okay. So actually let me take this as maximum as 10. Sorry, major as 10. Let me take this as 5. And tick marks. Inside. Okay. So see, D10 is the value of is the diameter 10% of the whole, like diameter below which 10% of the percentage finder is present. So this is D10. This, sorry. Similarly, this will be our D30, and sorry, this will be our D60. Okay. Till here. This will be till here. Let's draw the vertical lines also. Actually, what we should have done is taken rectangles, because then it would have given us both vertical and horizontal lines. Let's try to do that. Let's have no fill, and let's have a shape outline. Okay, so our 10% will be at here. Here. We will have our 30% will be here, and then we will have our 60%, which will be here. So let's also have tick marks in on this axis, so we can see. And major at 1, minor at 1, 0.1. Okay, these are the units. Okay, so let's check if this is D10, this is 0.09. So our D10 will be 0.09 mm, and this is D6, D30. This is 0.1, 0.2. Do we have a tick mark there? Yes, we do. So this is D30 will be 0.2 mm, and D60. Let's see where D60 is crossing. This is D60. So let me do one thing so that you have a better representation. Let me change the color. Let this be green. Let this be yellow. And then let's give these the same colors. This is green. This is orange. Okay. So D60 is 0.1, 0.2, 0.3, 0.4. 0.4 mm. So we have calculated, we've completed the second part of this question, and we have calculated D10 as 0.09 mm, D30 as 0.2 mm, and D60 as 0.4 mm. So now let us calculate the CU and the CC. So you know that CU is equivalent to D60 over D10, which will be 0.4 over 0.09, which is equivalent to approximately 4 point, 1 second, let me check, 0.4 over 0.09, 4.44. This is CU. Now let's calculate CC. CC is D30 square over D60 into D10, which will be equivalent to 0.2 squared over 0.4, 0.09. This is equal to 1.11. So let's write here. Actually, let me do one thing. And let me write the answer here. Cu equals 4.44 and Cc equals 1.11. Okay, so that is our question number one. We've completed all the four parts. Now let's move on to the next question. So in the next question, it's almost the same, but you will have results of the sieve analysis and hydrometer analysis. So we have data for sieve analysis as well as hydrometer analysis. And what are we to do? Plot a combined grain size distribution curve, and from the plot determine the percentage of gravel, sand, silt, and clay. Okay, so let's move on to this question. Let me write this as question 1. Now let's move on to question 2. Okay, okay. So for this question also, let us copy the data to our Excel worksheet. So in this, we don't have to do the calculations because we have been given the percentage passing itself. Let me actually take this here. So from Till here we have hygrometer analysis. So this is hydrometer analysis. And this is sieve analysis. This. So we have a percentage finer, percentage passing. Here we have percentage finer, but sorry, for the upper part we have, for the sieve analysis we have percentage passing. So we have to calculate the percentage finer. So percentage passing basically is percentage finer. So all we have to do is just plot the graph. So let me do one thing. Let me take this from here and let me just change the data. So move this and let's add particle size distribution curve, x value and y value. This seems to be an issue. Let me check. Okay, so there are two outliers in this data. Let me change the graph to here. Okay, and basically what's trying to say is that in experimental data you will not get a very smooth curve all the time. So sometimes what you have to do is you have to ignore some of the outliers. So here how we can do this is, so we don't need this, we don't need this, and we don't need this. And what we can do here is we can take a trend line. So we can have a moving average kind of thing, but that is not what I am after. Oh, there's a problem with my writing board. 1 minute. So what we will do is we will consider this point as an outlier and we will draw around this point our particle size and even this point. But if I see what the text that I am referring to, BM Das, what they have done is they have taken this point as well as this point as outliers. So let's see what we can do. We'll uh, draw two graphs. Okay. Oh, no. Okay. So in the first graph, let's skip this point. This is 0.075. Okay. And this point, this is 0.25. Okay. So what we can do is edit 0.25 we don't want. So we will take 0.75 also we don't want. Yeah. And this. Okay, this is name. PSDC. Sorry. We'll take this and we'll not take 0.25. Then we'll take this and then we'll take this. And for the Y, we will take this, then this, then this. But we also want to draw the outliers, so we will add outlier 1, which will be this, and Y will be this. Okay, and then there is one more outlier, which is this, this. Okay, so these are the two. Okay, so these are the two outliers. Sometimes this is what you have to do. You have to inspect. You have to inspect your data and see um, with like you see you get a smoother curve. And when I'm referring to the book, let me check. What they have done is that they have ignored this value as well as this value, like the first two values of the hydrometer analysis. Let's draw that also. So we will have the data. This value is 0.08 and 0.05. Okay, so we will have this and this, and the y direction we will have. Oh, this is also omitted. This is 0.25. Okay. Mhm. This, mhm. Oh, this, and the x we will have this, this, and this. I think there is an issue. Let me check. We add and select the data, and we will have this is what we are taking. And this is what we are taking. Then what seems to be the issue? Okay. Let me try to add the outliers. And let's add the outliers. Outliers will be this. Okay. This. Oh, okay. And this. Okay, that's fine. Um, okay. So this is the other graph that we can obtain. Okay. So what's the next part of the question? Definitely we've drawn the curve. Let's stick with this curve. This seems better than this, and it has only two outlier values. Let's stick with this. Okay. So plot a combined grain size distribution curve. We did that, and from the plot determine the percentage of gravel, sand, silt, and clay. So how do we do that? We have to know like what is the percentage, what is the diameter at which like you will classify at gravel, and what's the diameter for. Okay, so what is the diameter for gravel, what's the diameter at sand? So we will have gravel, sand, clay, and silt. This will be greater than 2 mm, we can say, and we will have 0.075, and this, then we will have less than 0.002. This will be greater than 0.002. Okay, so let's draw that in our curve. Like 4.7, I think gravel is So this will be, let me actually take a dashed line. This will be 2 mm, isn't it? And then we will have 0.075. This is point 0.1, point 0.01, point 0.02, point 0.03, point 0.04, point 0.05, 6, 7. This is actually 0.075. Then we will have one at 0.002. This is 0.001, this is 0.002. Okay, I can do this with the same thing for, I can do the same thing here. Okay, so we have 0.075 and then we have 0.002. Okay, so the question asks us what percentage is gravel, what percentage is sand, what's silt, and what is clay. So we can say, this is 0.075. So what we can say is, let me actually take a shape. Let's or let's give it a transparent fill actually. So this is just for to make you understand like how this works. That is why I'm using all these tools from Excel. Uh, so this will be our sand portion. Okay, this will be our gravel portion. This will be our sand portion. This will be our clay portion. And then this Finally will be our silt portion. Use different colors. So this will be gravel. There will be sand. This will be clay. And this will be silt. Okay, so this is basically how our chart will be divided. And if you want to calculate this, like we will get a little bit different results for these because of these outliers here. But you get the idea how we do this. So this will be, if we see percentage passing for gravel will be below percentage passing gravel is 92%. So gravel will be 8%. And then sand, let us assume that we have taken this chart here. I can transfer this also there. The gravel will be same. Sand will be a little different. Don't worry about this. This is not something that will be asked in your exams. But yes, this is a very this is a quite a possibility that you will face this kind of problem in your lab where everything is not theoretical. Most of the things are practical. So yeah, okay. For this, sand will be 0.75 is 31. We will have like this will be 92 minus 31. Sand will be 61%. Silk will be oh, I have actually done this and the error. After sand, we'll have silt and then we'll have clay. Okay, so the silt will be 0.002 is that like almost 10%. So it will be 61 minus 10. Sorry, 31 minus 10. Let me actually write this also. 100 minus 92. This is 92 minus 31. This will be 31 minus 10. Will be 31 minus 10. And then clay will be, excuse me, 10%. And the total for this will be 100%. And if we go with this portion, we'll have almost, instead of 31, we will have 38 here if we go with this diagram. But you get the idea behind that. Okay, so let us now take these values to our main PPT. So what we are getting is this is 8%. We have this at 61%. Let me correct this. This is at 21%, and this is 10%, and total we have 100%. Okay, so this is about question number 2. So let's move on to the next question. Okay, so the next question is about consistency limits. Okay, okay. So what we need to calculate following are the results of a test conducted in the laboratory. Determine the liquid limit and the flow index. Flow index. Okay, so as you must have studied in the first week, the liquid limit is calculated through a graphical procedure. So let's do one thing. Let's take another sheet for question 3 and let's take these values. So for liquid limit, what we do is on a semi-log graph paper, we plot the moisture content versus the number of blows. So let us first draw a plot. So on the x-axis, you will have the number of blows. On the y-axis, you will have the moisture content in percentage. let us do one thing so that you don't get confused. Let me add axes titles. This is, sorry, number of blows, and this is moisture content in percentage. And let me just quickly add axis titles to all the graphs. Mm, no, let's just keep it like this for now. I can reduce this. Uh, this was at 60, and this was at 30, and this was at 10. Okay. I'm sorry for this. Oh, something happening to the plot. Okay. So from this, you will get the idea for the next one. I will not include the titles here. Okay, so let us change this to logarithmic scale, as I mentioned that this has to be in log scale. Okay, and let's start from 10 to 100. Okay, let's not. Okay, so we have this. We have major at 20, minor at 10. Okay, okay, I can't seem to find the vertical red lines. Okay, what about the horizontal value of red lines? Okay, I've not, I think I have, minor, let's take at 10. Okay, okay, let's take this at 10. Sure, let's take this at 1. Sure. Okay, so what we need, sorry for this derailing, but sometimes we get confused in the formatting. Okay, so following are the results of the test conducted in laboratory determine the liquid limit and the flow index. So you know that the liquid limit is the water content at when the number of blows is 25. So this is 20. Let's go to 25. Also, we need to calculate the flow index. Flow index is just the slope of this graph. We can do that. Just let's take open. We need this at 20. This is 25. Let me take minor grid lines at 5. Okay. So tick marks inside. Okay. So the color, let's take black. So we can see. Okay. So this is approximately 25, and we will get about 39, 40. It will be like 39, 40. What we can do is we can change this from 35 to 50. Okay. Then here it's like 39.5 is our liquid limit calculated from the graph. Let's take it here. Okay. So our liquid limit is 39.5, and our flow index is just the slope of the graph, which will be W1 minus W2 over log to the base 10 N2 over N1. Let's take this as, let's take these two values, 42 minus 39.3 over log to the base 10 28 over 15. So let's calculate. We will get a value of 9.96. This will be the IF value for our soil. Okay, so now let us move on to the next question. Following are the results of shrinkage limit test. This is the initial volume of soil. Give me a moment, please. Okay, so this question is on shrinkage limit. Initial volume of soil is given in saturated state. Final volume of soil in dry state is given. Initial mass in a saturated state is given, and final mass in dry state is given. So we have to determine the shrinkage limit of the soil. What we can do with this question is we can try to draw the phase diagrams. Okay, so let's try to do that. So we will have, let's draw the phase diagrams so that you can better understand what's happening. Okay, if this is the total volume initially, this will have some solids and this will have some water initially. And when we dry this, the volume of solids will remain same, but the volume of water will be removed. Uh, Let me do one thing. Let's take this as water. Let's take this as soil. Okay, this will be again our soil. Where did it go? This one. Okay, and this will be our air. Let me denote air like this. Okay, so we will have air, water, solids, and then we will dry it. We will only have solids and water. And if we draw the, this is the phase diagram. If we draw the, let me take it from here actually. Let's not draw it. Let me show you. Okay, so this is the volume of soil and mass of soil before drying, and this is the final volume and final mass. Volume 1 is volume of all these three, and volume 2 is this, like, and then we will have M1 will be this plus this, and M2 will be only this. Okay, okay, so in saturated state, this is the three-phase diagram is for unsaturated state. But what we do in this is first we saturate the soil. Let me write this here. This is unsaturated state. But we are taking the soil in saturated state. So what will happen is that all of these voids will be filled with water. And this is not necessarily the maximum. The This is not necessarily like at shrinkage limit, and we will have a volume minimum. At shrinkage limit we will have something like this. The Okay, so this is unsaturated state, this is saturated state, but liquid limit is greater than the shrinkage limit. Sorry, the water content is greater than the shrinkage limit. Here, if we say that this is the minimum water content that the soil mass requires to attain saturated state, then when we dry this, this is the dry state. Okay, so initial volume of wet soil part, this is the V1. Final volume of the soil will be here, and if we want to calculate the shrinkage limit, we have to take okay, shrinkage limit is the water content here, isn't it? So we can say if this is M1 and this is M2, this will be M1 minus M2. See here you have this air, M2 will be only this will be M2, this will be M2. Okay, so shrinkage limit will be M1 minus M2 over M2 into 100 minus Vi minus Vf over M2 rho W into 100, where rho is the density of water. So this is V1 and this is V2. Okay, initial volume of soil in saturated state V1, final volume in dry state V2, initial mass in saturated state is M1, final mass in dry state is M2. Okay, so what we want to determine is the shrinkage limit. So it will just be equal to, from this formula here, the shrinkage limit will be equivalent to M1 which is 544 One second. Okay. This is an error here. This is equal. Okay. So let's calculate. This will be equal to 44 minus 30.1 over 30.1 into 100 minus 24.6 minus 15.9 over 30.1 into gram per cc, 1 gram per cc into 100, and the saturated the shrinkage limit will be equal to, let me calculate, which is 17.28. So basically, let me show you what this formula is doing actually. You have these consistency limits, you will have, sorry, water content here, and you will have volume change here, and these are the consistency limits. This is the shrinkage limit, and you will have a plastic limit here, and you will have a liquid limit here, and we saturate it beyond, like, oversaturate it. And if we say the initial water content was here, and this is the water content, extra water content above the shrinkage limit, what we are calculating is Ws equals Wi minus delta W. So Wi will be, W is the weight of water over weight of solids. Here we saw weight of solids was M2, and weight of water is M1 minus M2, as we saw here, M1 minus M2 and M2. So the water content here is Wi equals M1 minus M2 over M2 into 100. So this is the water content here. This is the first term here in this equation. This is the first term, and the second term is delta. W, which is like the water content which is above and beyond the shrinkage limit. This will be equal to the change in volume um, from initial to here, this part. The change in volume that you see multiplied by rho W, you will have the weight of this water that we want to subtract. Okay, so what we are taking is Vi minus Vf, so we get this Vi. Uh, so this is V initial minus V final, and because we want to subtract this, so we will subtract from this what the weight of water we will get here over M2, and that is what we are calculating here. Wi is the initial water content, which is M2 minus M1 over M2, sorry, M1 minus M2 over M2 into 100 minus the water content that is extra, which is Vi minus Vf into rho W into 100 over M2. And that is what we have calculated here for the shrinkage limit. So that question was for the shrinkage limit. So let me check. I think we have some time left. Yeah, we have some time left. So what we will do is we will do a question on the classification of soil. Okay. So let me get back to you on that. Let me do a question on the classification of soils. Okay, so I have added some questions for classification of soils. Let's go through them together. So the results of particle size analysis of a soil are as follows. Percentage passing through soil, sieve number 10. One more thing that I wanted to mention was that more often than not, instead of the opening size of sieve, you will be given the sieve number, and you should know what opening size these sieve numbers designate. So there is this table that you can refer to, and some of these values you should know by heart. For example, 4.75, you should know the 2 mm, you should know the 0.075, that is sieve 200. So these you should know. Okay, so actually let me highlight this. So you should know these. And sometimes even this helps. Okay, so okay, so sieve number 4 is 4.75, sieve number 10 is 2, sieve number 200 is 0.075. Let's go back to our question. Sieve number 10 is 2 mm. Sieve number 40 is, we did not check, this is 0.075 mm. and this is 4.75 mm. Let's check together. See number 40. Okay, 4.75 is see number 4. This is 425. 0.425. Okay, let me correct this. 0.425 mm. The liquid limit and plasticity index of the minus 40 fraction, minus 4.25 fraction of the soil are 30 and 10 respectively. Classify the soil by the unified classification system. So you see there are some steps that you have to follow. Um, like it's kind of a, what can I say? It's kind of a flow chart that you may be uh, aware of. Like first you have to check if this is a fine grained or a coarse grained soil. Okay, so percentage retained on 0.075 is 58%, which is like, let me refer to the chart that you have studied in class, because there are some minor differences in the system for IS classification system, and let us follow what you have studied in class. Okay. Huh. So the IS classification system, we will do the IS classification system and not the USCS system. So there is a two-letter system. First one defines the soil type, and the second one defines the subgroup. Steps: determine whether the soil is of organic origin or coarse grained, fine grained. Organic soil is organic soil is identified visually. So there is nothing written about organic soil. So let's move on. If 50% or more of the soil by weight is retained on 75 micron sieve, which is hair, 50% or more, it is coarse grained soil. So number one criteria, percentage okay, retained. This is percentage passing. Okay, retained on 75 micron sieve is 100 minus 58, which is equivalent to 42. 42%, which means that this is a fine grained soil. The first part we have identified. Now let's move on. Okay, this is one second. If we move on based on what has been taught in class, this is the second part. The first part is soil is not of organic origin. Second part, 50% retained on 75 micron sieve is 42%, which is less than 50%. Therefore, soil is fine grained. Okay, so let's move on. Right now, let's go to the next step because the soil is not coarse grained in our case. If the soil is fine grained, determine the liquid limit and plastic limit on the soil fraction passing the 425 micron sieve. So, sieve number 40, we have, oh, sorry, we have been given the liquid limit and the plastic limit. We have determined the liquid limit on the 425 micron sieve, passing the sieve, which is 30, and we have been given the plastic limit, which is 10. Next, if the limit plot the A line, classify. Okay. Um, Now, what is the formula for our A line? If the first let's check the A line. Okay. P I equals 0.73 liquid limit minus 20. This comes out to be 7.3. But our liquid limit that has been given to us will be our plasticity index, the plasticity index of the soil calculated P experimental Pi experimental equals 30 minus 10, which equals 20, which means that the at the liquid limit is 30. Let me transfer this here actually for you to understand better. Okay, so our plasticity index is 20 and our liquid limit is 30, isn't it? So this is our plot, and the A line is at 7 point, how much did we calculate? 7.3. Yeah. So it is greater than 7.3. Our plasticity index is greater than 7.3. So this lies in the clayey part. Second thing that we have identified is that Pi is above A line. And also we need to check if the liquid limit, if it is between 35 and, okay, if it is between, so liquid limit is 35 or 50, then we we assign dual symbol, but because it's not close to this line or this line, so we will say that we have a clayey soil of low consistency. So our classification will be CL, clay soil of okay, low consistency. So that is how you go on for your soil. Now, if this was coarse grained soil, let me check if I have a question on coarse grained soil. Okay. So let's go on to the next question. Let me check with the time. We have a little bit more time. We can go on to the next question. Let's go on to this question. So this figure gives us the grain size distribution of two soils. The liquid and plastic limits of the minus 40 C fraction are given. Determine the group symbol and group names according to the, let's say, IS system here. So the sieve number 200 is 0.075, or 75 micron, and as we can see that the percentage finer than 75 micron here is 60%, and here only we have about 10%. Okay, so we write here for soil A, if we see sieve number, so this is coarse grained soil because only 10% is passing, which means 80% to 90% is retained on this. So this is coarse grained soil. First thing is percentage finer than 75 micron is less than 50%. So this is coarse grained soil. Second thing that we have to check is C number 4 is 2 mm. 1, this will be 2 will be somewhere here. So the percentage retained on 2 mm is 0. So we can say this is all sandy because gravel will be here. This portion is all sandy. So we see second part. If we look at the notes also, after coarse grain soil, you have to determine if it is gravel or if it is sand. Okay. If the soil is coarse grain soil, obtain the grain size distribution curve. If 50% of the coarse fraction is retained on the 4.75 sieve, uh, classify the soil as gravel. Okay, they have gone with 4.75. Still, it will be the same. Our soil will be sandy. If the soil fraction passing through the 75 micron sieve is less than 5%, determine the gradation of the soil, but it is not less than 5%. It is about 10%. Okay. If it is more than 12%, perform the liquid limit and plastic limit tests. If it is between 5 and 12%, soil is assigned dual symbol appropriate to its gradation. Okay. And plasticity characteristics. It is between 5 and 12%. So first let us determine the gradation of the curve of the the curve. We have D60, D30 and D10. Let me give you the values. D60 equals 0.135. You can read it from the graph. D30 equals 0.12 and D10 equals 0.085. So let us now calculate the Cu and the Cc. For soil A, Cu equals 1.59 and Cc equals 1.25. This is greater than 1, but this is less than 6. So it is a poorly graded soil. And you did not have to, like you can even see it from here. This is a poorly graded soil because, um, see, kind of a uniform, uh, uniformly graded soil. It has more particles with a certain diameter than the rest. Okay, so now we have been given the liquid limit and plastic limit. So let's calculate. The liquid limit is 30, plastic limit is 22, IP is 30 minus 22, which is 8. Let me write here. For soil A, actually let me write here. IP will be 8, here it will be 6. And if you go back to this chart, the liquid limit is 30, IP is 8. 30 and 8. It is just here. The first soil. The second soil is soil B, 26 and 6. This is somewhere here, CLML. This is soil A, this is soil B. Okay, so This is just about this. Actually, let us calculate 0.73 WL minus 20. WL is 30. 0.73 into 30 minus 20 is 7.3 IP here, and we have 8. So it is clay. The soil A is clay, and soil B is 0.73. 26 minus 20, it is 4.38. This is at 4.38, and we have, okay, both of them are clay, clay silty. Okay, so let's move back here, because the percentage finer is between uh, finer than C200 is between 5 to 12%. So the first, it will have a dual symbol, soil A. It will have sand, poorly graded, and sandy clay. This will be the classification for soil A. And if you go for soil B, we see that it is basically 60% is passing through the sieve number 200. So this is fine grained soil. This is coarse grained soil. Okay. And for soil B, we calculated, we get CLML, but let's check. If the soil is fine grained, determine the liquid limit and plastic limit of the fraction that we have determined, and we check the plot. Uh, if the uh, if the limits plot a line classify, if liquid limit is between now, if liquid limit is greater than 50, classify MH, that is fine. If the plot is in hash zone, which is the case, classify as CLML. If the limits plot close a line, uh, so we already have CLML, and yeah, so the second soil will be CLML. Soil B is CLML. So there is one more question that I think that you can try on your own. So I will be leaving it in this PPT that I will be providing later for your reference. I'll be leaving it. You can try it on your own. And I think that is it for today. Thank you very much. I hope to see you in the next session. With interaction, this class can actually be something else. So I expect to see you in the next session, and good learning. Okay.